Okay, so we're open for review now. I think, Ashley, you had a question on it was a 10.4 problem, actually. Okay. It was page 512, number 7? 7. Okay, so the question was, I'll just start typing it in here. It'll be easier to follow along if I type it in here, I think. Okay, so this is problem 7, page 512. Okay, so it says here the the null hypothesis is sigma equals 4.3. The alternative hypothesis is, oh, sorry. Yeah, thanks. The alternative hypothesis is sigma does not equal 4.3. So it's a two-sided test. Random sample n equals 12. From populations is known to be normally distributed. Very important phrase there. A lot of people gloss over that. So the fact of the matter is my sample size is kind of small, right? How big should it be normally? It should be 30, but since they told me it's normally distributed, I don't need to do my QQ plot and check it. So thank you. Just saved me a step of a QQ plot there. All right. So it's known to be normally distributed. Okay, if the sample standard deviation is known to be 4.8. I'll make that a little bit bigger. Compute the test statistic. Compute the test statistic. Okay. Well, this is pretty nice. I'd probably like, okay. Let's go all through the 7 steps, even though really they're asking you for step 3, right? Right off the bat, they're not making you go through the first 2.
I think she asked for number 6. Instead of number 7.
I didn't do number 7, but what I like finding the hypothesis, like the probability with like.
See, normally I would treat this just as a hypothesis test. I would just give this all to you, and I would say, they're just anyway. So rather than compute the test statistic, let's go through the 7 steps, which will answer all their questions anyway. Okay. So the first question is this quantitative, categorical, or regression? This is definitely quantitative, right? The second step would be, what kind of a test statistic is this? Actually, you kind of need that to know the question they asked. Is this a z, a t, a chi-square, or an f? It's chi-squared. Have we only learned one chi-squared test? We're going to learn more. So let's be a little bit more. So yes, it is chi-squared. Which one? There's only one that's quantitative. You're looking at the outline. Yeah, that's helpful. Okay, you won't be able to get that on the test though. Okay, got to memorize that outline if you want to. So it's a 1 standard deviation chi-square test. Okay, useful information to actually answer the question, which is actually step number 3, compute the test statistic. Okay, so if I'm answering that question, what's the equation that I'm going to be using? N minus 1 times s squared divided by you said standard deviation, but which one? Sigma squared. Okay, that's the equation I'm going to use. I'll underline it so it looks like a fraction. So my n minus 1 is going to be 11 times my s, which is 4.8 quantity squared, and my denominator is equals 4.3 quantity squared. Where did you get the 4.3 from? The null hypothesis, right? Okay, so the test statistic, the answer to part A is simply that divided by that. 13.7. So that's the answer to part A. Okay, that's part A. And now, what's part B? If the researcher decides, part B, if the researcher decides to test at alpha equal 0.05, determine the critical values. Now, what would I ask? Well, there's a reason I didn't assign this problem. You're doing a problem that I didn't assign. Because you can't find the p-value on a two-tailed test. Normally, I would ask you for a two-tailed. So if that makes you feel any better, I'm not going to ask you a hard question like this. If I did, the really only way to do it is to draw a picture. So let's draw our picture here. Okay? And determining the critical values is very important if you're going to draw your picture. Okay? So how would you draw the picture of this one? So the picture is what they call the classical method. You're welcome to know the classical method, but I'm not going to ask you to detail test on the chi-squared. Okay? So I need some sort of a chi-square distribution, right? Now, if my alpha equals 0.05, how much do I have in each tail? I've got 0.025 in each tail. So this is alpha over 2 equals 0.025, and this over here is alpha over 2 also equals 0.025. So I've got to find those two critical values. That's the answer to part B. Okay, how do I find that? Now I could do it with either the computer or with the, well, or with the, I guess I answered my own question there. You're supposed to answer that. I waited too long. Or with the, fill in the blank. With the what? Longhand writing it out. Chart in the back. That's what I was looking for. Okay. So let's go. So in fact, you'll get slightly different answers whether you use the computer or the chart in the back. We'll do it both ways. Let's share our screen. If we're doing the book or the chart, I'm going to need the lower and I'm going to need the upper. And if we're going to do, here, I'll write it this way, the chart or the computer. Okay, let's look at the chart. That's probably easier to visually remember. So if I open this up, how would I use the chart? Here we go. Maybe I'll leave that there for a minute because remember, whenever you're using the chart, it's important to look at the tables. What is the chart telling me when they give me an alpha? Give me the right side or the left side? The right side. You're giving me the right side. Okay, so okay. So looking at the chart, they're giving me this number. Okay. So which column am I looking at? Okay, you told me the row. Okay, Victor said the row is 11 degrees of freedom. 0.05? 0.025, right? Because I got to split that in half. Okay. So in the table, 11 degrees of freedom, that gives me 21.920. Okay. So this value here on the right is 21.920. How do I find the value on the left? 0.975. Okay. 11 degrees of freedom, that gives me 3.816. 3.816. Okay. So if I'm using, so those are my, so to answer that question with the chart 3.816 on the left, well, let's say 21.920 on the right. Okay. How would you do this with the computer if you're using the computer? I don't know. Chi-square, which one? Is it dist or inverse? It's inverse, right? Now I got inverse and I got inverse right tail. What's the difference between those two? Inverse is going to be the left tail. Okay, it's asking me for a probability. What do I put in there? What is it?
Your output.
What?
Your output.
Mm-hmm.
So 0.025.
0.025. And degrees of freedom, 11. Hopefully I'm going to get an answer very close to 3.816. How about that? Okay. What do I do for the upper? Chi-square inverse right-tailed. Then the probability, what's the probability I put in here? 0.025. This one's actually easier than the chart, isn't it? You just put in what you want. And degrees of freedom, 11, 21.92. How about that? Okay? So that was part B, yes?
So on a computer, like, and with all the tests, I don't understand the difference between using this function and the inverse.
Okay? That's a good question. For those of you at home who are listening, the question was, she doesn't understand the difference between dist and inverse. What is the difference? Because you have T dist, you have T inverse. You got chi-square dist, you have chi-square inverse. What's the difference? Now, let me say this. When you're typing it in, if you're paying attention to what it is, if you're not sure, let's pretend. So I know it's chi-square something, right? Chi-square something. I'm not sure if it's dist or if it's inverse, okay? We know it's inverse because I just showed you. But what happens if I do dist? Okay? Dist is asking me for x. Okay? What's it asking me for? What does x represent in this case? It's going to represent, somebody said z-score. It's not a z-score. It's a chi-square score. So it's looking for a value greater than 1. Okay? Now, if I go chi-square inverse, this one's a little bit more obvious because it asks you for a probability. Okay, so they are actually inverse functions of each other. If it's asking for a probability, that's got to be a number between 0 and 1. You put in a percentage probability of something happening, 2.5%, 5%, whatever. It's going to give you the chi-square score, a number greater than 1. Okay, so this is going to give you numbers on the bottom of the chart. Okay, if it's asking you for the distribution, it's looking for a number greater than 1, and it's going to give you the shaded area. And that's true for any function. Inverse gives you the scores on the axis. This gives you the area of the shaded part. Does that make sense? So that's going to be universally true, whether it's T dist, T inverse, chi-square dist, chi-inverse, anything like that. Okay. All right. Very good question. I know people get confused. That's how that works. Okay. All right. So depending on that, so that's answer B. Answer C. Draw the chi-square distribution and depict the critical regions. We've already done that. That should have been part A, not part C. Okay. What were they thinking? And part D, will the researcher reject the null? Actually, there's one piece on this picture that I did not finish. Okay, what needs to be added to this picture? I'm going to let you look at the spreadsheet before I blow this up, because it's something from the spreadsheet is going to need to be added to this picture. What needs to be added?
The new standard deviation.
No, not the new standard deviation. The test statistic. The test statistic is, in this case, is from part A, right? It's in yellow. It is 13.7. So if I stop sharing here and go back to my picture, 13.7 fits in between these two values, right? 13.7. It's a 3, by the way. Okay. So is 13.7 in my rejection region? No. So part D says reject or do not reject. Do not reject. Okay, now they didn't ask you for a conclusion, but I will. Guaranteed I will ask that. What would be really question E, the conclusion? What's the conclusion?
you.
There is not enough evidence that see, a lot of times they say you write this in terms of the alternative hypothesis, and sometimes that can get crazy. But there's not enough evidence that
You can get rid of 13.7.
no 13.7 has nothing to do with it. What's our null hypothesis?
So he showed
Our null hypothesis. Let's go back here. We got to review this. The conclusion is always about your hypothesis here. If I go back here, this is my null, this is my alternative. We do not reject the null. Okay? That means we think the null is probably true, or there's not evidence against it, right? So the conclusion is there is not enough evidence that sigma is different than 4.3. Now, let me tell you a common mistake. I usually don't tell people this before the test. Okay? I'll write this down. Some people may say, and you tell me if this is right or wrong, there is evidence that sigma equals 4.3. Is that a correct conclusion? No. In fact, our evidence was it was 4.8, right? We have evidence that it's against. It's not 4.3, it's 4.8. According to my sample, it's 4.8. Is this a correct conclusion? No, this is what I would say. This is too strong a conclusion, okay? You can't make that conclusion. It's better to say there is not enough evidence that sigma is different than 4.3. Well, we got a different value, 4.8, but we're saying that's not significantly different than 4.3. It's too close. Does that make sense? Okay? So some of you are going to make too strong of conclusions. Don't be too strong. Okay? It's not significantly different than 4.3. Okay? Very good question. Oh, that took up almost all the time. Now, what other questions do you have? Yes.
I'm still confused about drawing a picture. Probably for 10.6.
Okay.
I guess one example would be
So she's still confused about drawing a picture for 10.6, which is the type 2 error. That's what you're really asking about. How do you draw a picture? Should we just concentrate on the picture because we've only got about 6 minutes left? Okay. Do you have one?
we do number 6.
Number 6, you just want to draw the picture? Okay. So this is a hypothesis test for standard deviation. So the next one is, and I'll draw the picture. Do you want me to draw the picture on the computer or on the board? It's a little look better on the board. Okay. All right. But I will do this. Okay. So number 6 says we're testing the null hypothesis that the null hypothesis is P equals 0.75 versus the alternative hypothesis, which is P less than 0.75. Okay, so here's what I would say. Since they gave you the only alternative, you can already start drawing the picture based on just that. Okay? Maybe we'll just go back to the board. We'll just do this as a board thing. So I've got the null hypothesis, P equals 0.75 versus the alternative hypothesis, P less than 0.75. Okay? What am I drawing? Based on the null hypothesis, what should it be drawing here? What? The left side? Okay, before I draw the left side, what's the mean?
Oh, I'm sorry, I mean,
The mean is No, it's not 0. It's 0.75. Okay, we are doing a left-sided test. I don't think they gave me an alpha yet, but you can already, just based on the null hypothesis, you can draw this. Okay, this is number 6. Simple random sample n equals 400. That's important information. X is obtained with 280 successes. Okay. What does it mean to make a type 2 error for the test? You just want to do the picture. Your alpha is going to be 0.01. So our alpha equals 0.01. Okay. Compute the probability of a type 2 if the true proportion, probability of a type 2 if the true proportion equals 0.71. Now, the only thing that's a little bit tricky about this is I don't know what the rejection region is. Okay? Until I solve for that, I don't know if 0.71 is in the rejection region or if it's not. To some degree, it doesn't matter, but it kind of does matter for your picture. So I'll do it 2 ways. If 0.71 is in your rejection region, I would draw a mean with 0.71. In this case, I'm only taking the type 2 would be this area to the right here. This is your beta, which is your type 2 error. Now, the other way I could draw this, maybe I'll just draw a new picture so it's more clear. Okay, 0.75, this alpha equals 0.01. I don't know what that value is yet because I haven't calculated it. But if 0.71 is here, okay, I'm still going to draw my normal curve in this case. I'm still drawing this area here. Okay, this is your beta, this is your probability of your type 2 error. So as you look at these side by side, visually, which one has the bigger beta? The one on the right has the bigger beta, right? Because it's closer to 0.75. This one's got a smaller beta because it's farther away from 0.75. Okay? Does that help, Samantha?
So if this is left tail, if it's right tail, is theta going on?
If it would be right-tailed, yeah, everything would be a mirror image.
And then
What if it's two-tailed? If it's two-tailed,
Would we see a two-tailed?
a picture of a two-tailed?
Well, we're gonna have to do one for a test.
Probably. Okay, so we're going to have either a p or a mu here, whatever it is. Depends on whether it's a distribution. In this case, if I'm doing this here, you're doing a two-tailed test here, right? Now, the question is, I need to figure out these values. Obviously, I can't do that, okay? Now, you realize the closer either p hat or x bar is, or the alternative hypothesis is to the mean, the bigger your error is going to be. Okay? If you're in the tail, it's not going to be as big of an error. Okay? I don't know where to draw it because this is just a made-up problem. Okay? I'm going to draw it right here. Okay? This is either our new p or our new mu. Okay? If I'm drawing a curve here, I'm probably going to want to draw it like this. Okay? I'm looking for the area between the two rejection regions. That's going to be your beta. Okay? So it's going to stop. It's going to stop at whatever the rejection region is on the right in this case. Okay? Now, if it's farther away, obviously, the farther away your red distribution is from the black distribution, the smaller your beta is going to be. If it's clear over here, it's going to be a very small beta. If it's clear over here, it's going to be a very small beta. Okay. And in fact, maybe just for fun, if I were to draw it here, let's draw it this way. This is another two-tailed. This is either your P or your mu. You're going to draw in your two-tailed thing here. Okay. Let's put our new P right here. I'll put it right here. Okay. going to be like this. It's going to be like that. Always draw it into here, okay? In this case, your beta is going to be this area here. Okay, it's going to stop. It's going to stop there though. Okay, it's going to stop here. It's always between the rejection regions of your type 1. Okay. So without numbers, that's kind of the best general rule I can give you. So, all right. So I'm going to post this. Pretty sure the other class is going to have different questions, so I will post both reviews for you. You can hear what their questions are. Okay. See y'all tomorrow. Good luck on the test.